after those 5 consecutive ones. In a discussion which I had with Dr. Wu in one of the meetings which I had during his office hours, he said that instead of using bit stuffing, it would be a better idea if we use bit scrambling, right? Because bit scrambling does not add redundancy to your system, and it will give a better performance in those terms. Since I was running out of time and since this had already been implemented, and the change in this module would mean that I changed the entire decoding system, I actually just went with bit stuffing. But just as a suggestion to the listeners, it's really important that instead of bit stuffing, we could actually use bit scrambling. Again, we have the TRELLIS encoding, which is nothing but a convolutional encoder. And then we do an NRZ encoding on it, we do the modulation, which is the BPSK modulation in this case, and then we transmit the data through an AWGN channel, and then this signal gets transmitted over the channel. So all these different blocks, these are designed in MATLAB to do the simulations, and then we produced some really good results, which I'll be showing in the subsequent slides. So these are the test conditions. We are using a CRC generated polynomial of order 16. We have bit stuffing. We have the TRELLIS encoding, which is nothing but the 214 convolutional encoder. We have the modulation technique as BPSK. We have the bit rate as 1000 bits per second. We have the amplitude as 1, and then the channel which we use is AWGN channel. We vary the noise variance over a set of values, and then we take a look at the results, how varying the noise variance over this channel would affect the bit error rate, the packet error rate, the EB by N naught ratios, and things like that. So again, the packet size for these computations is 100 bits. I would like to mention the fact that these 100 bits, this is not a very realistic number in terms of doing a realistic simulation, because generally in the modern communication system we use very long packets, not as small as 100 bits. But still, just for the sake of some analysis, we are using 100 bits. Again, another reason of using a small packet size was we did a lot of exhaustive simulations, and then the simulations would run overnight or on the servers. So that's why we reduced the packet size to 100 bits to reduce the simulation time, so that we can get the results quickly. So before going into the details of this error correction technique, I'll have to give you a brief background of how the TRELLIS encoding part works. So here the TRELLIS has 8 states. I'll assume that the listener has got a brief understanding of how the TRELLIS encoding works, but still I'll quickly go over how an input stream is encoded into a TRELLIS kind of a structure. So now these are 8 different states that a TRELLIS can have. It means that this TRELLIS encoder will have 3 memory elements, and these 3 memory elements will have 2 power of 3, that is 8 different states. So now these are all the TRELLIS transitions. The dotted lines show that show the transition which correspond to an input of 1, and then these black solid lines show the transition which correspond to an input of 0. So if the input is 1, the TRELLIS changes state from 0, 0, 0 to 1, 0, 0, and the output becomes 1, 1. So here the code rate is 50%, as in we give in 1 input and we get 2 outputs. So the code rate is k by n, which is 1 on 2, which is 50%. So here we are adding double the redundancy. So if you see, the amount of redundancy is too much here. Again, there is one point which I forgot to mention in the previous slide when I was discussing error and when I was discussing channel encoding. What typically happens in a channel encoding scenario is that you have a stream of inputs, and then you add redundancy to that stream, right? So, but then how do you gain? How do you get the channel gain out of it? You're adding redundancy. It means that you're consuming more bandwidth and you're consuming more resources. But the gain here comes from the bit energy per symbol. So the energy per bit or the energy per symbol gets reduced when you have the error encoding in place. So now this is how we get the channel gain. Again, coming back to the TRELLIS encoding part, we have the input as 0. If we have the input as 0, the state remains 0 and the output becomes 0, 0. So this is how we traverse to the TRELLIS. Let's see how we'll encode an incoming bit of 1, 0, 1, 1, 0, 0, 0. So if you have an incoming bit of 1, your initial state is 0, 0, 0. You go to the next state, which is 1, 0, 0. You have the next input as 0. You have this transition from 1, 0, 0 to 0, 1, 1. You get the output as 1 1. So if the input was 1, the output becomes 1 1. Now the next input was 0, the next output is 1 1, and we keep on traversing through the trellis to encode, right? So this is kind of an on-the-fly process where, you know, depending on the previous state, we know what the encoded bit would be. So if the incoming bit is 1011000, then this would be the encoded bit. So let me quickly discuss the VITERBI decoding algorithm. So whatever we encoded using the trellis structure which we saw in the previous slide will be decoded using the VITERBI decoding algorithm. And first I would like to discuss the conventional VITERBI decoding algorithm, which is typically used in conventional decoders. And then we'll talk about the modified VITERBI decoding algorithm which we designed in MATLAB based on the paper which we referred to. So now this VITERBI decoding is the best known implementation of the maximum likelihood decoding process. So here what we typically do is we narrow down the total number of options that we have, and then we kind of propagate through the trellis. We keep on discarding some of the paths which we think are not the correct paths, are not the final paths, and then the entire process is done on the fly, right? But it's really important to note that there are two assumptions that we make when we use this VITERBI decoding algorithm. One is that we assume that the errors occur infrequently, which means that you don't have a burst of errors. And then again we will see some of the simulation results which will show that this VITERBI decoding algorithm fails drastically for channels which induce a burst error. So as I said, we assume that these errors are distributed randomly. Now let's quickly see how the VITERBI decoding algorithm works. We saw that we had transmitted this data stream when we did the trellis encoding. Now let's say that we received a data stream which looks something like this, where we have the error right at the first bit. Okay, so the way this VITERBI decoding algorithm works is, you see that your input that you received is a 0 1, right? So you start from the first state, which is 0 0 0. Okay, from the first state there are only two possible transitions that are there. So one is 0 0 and one is 1 1. But you have received a 0 1, right? So let's assume that, you know, it could go from state 0 0 0 to 0 0 0, or there could be another possibility where it could go from 0 0 0 to 0 1 to 1 0 0. So when we are doing the decoding, we assign some path metrics here, right? So these are the path metrics which we assign, which is nothing but the Hamming distance between the received code word and the two possible code words which could have been received if it was at state 0 0 0. So moving on to the next state, we see that from this node we again have two possibilities of transitions which are there, and from this node we again have two possibilities of transitions which are there. So here the possible transition is that your received code word is 1 1 and you do a transition from 1 0 0 to 0 1 0. So here we again assign some new path metrics. Again we compute the Hamming distance. Here the Hamming distance is, we compute the reverse of the Hamming distance essentially. We just see how many bits are matching, right? So we see that, you know, both these bits 1 1 are matching the received incoming bits. So we have a path metric which got increased to 3. So these are cumulative path metrics, and again the path which has the largest metric will be considered as the winner. So if you go on traversing through the VITERBI decoding trellis, what we see that there would be some paths which actually converge to a particular point. Here, as you see, these red paths are converging with these paths which have been represented by a solid black arrow here. So again, we keep on computing the path metric. So we see that the path metric for both these paths which are coming to this node is 2 and 5 respectively. So what we essentially do here is we discard the paths which have got the least metric at a particular node. So now in the next slide you see that we discarded all the paths which had a metric of 2, 4, 4, 3, 4, 2, 3 and 3 respectively. So we discarded those paths, and this is how we reduce on the amount of computation that we are doing in a VITERBI decoding situation. So again, we keep on traversing and we keep on removing the paths which converge to a particular point. So we keep on moving through this VITERBI decoding trellis, and we keep on computing the path matrices. So here you see that this path which is coming from here has a path metric of 7, and the other path which is coming from here has a path metric from here has a path metric of 8. So at each node we compute the path matrices, and we keep on discarding the paths which have the lower metric at one particular node, and then at the end we can see that this particular path right here has a highest metric, which is 13. So we will take this path and we will decode the VITERBI, we will So we will take this path right here, which is which has a path metric of 13. So we will take this path right here, which has a path metric of 13, and then we say that okay, now this path which has a path metric of 13 is the final path, and then this, and then all the code, all the received values corresponding to this path would be the actual received values. So this is how the conventional VITERBI decoding algorithm works. So now let's take a look at the implementation of the CRC in terms of a trellis. Now the good thing is you can implement the cyclic redundancy check in terms of a trellis, which means that you can represent the CRC in terms of a trellis diagram. Now this is the basis of this project, where we design a trellis diagram for the CRC that we are using. So here is an example trellis diagram for a CRC with a polynomial order 2. So it will essentially have 4 different states. So now the ability of CRC to be implemented in the form of a trellis is the basis of this paper. Now this paper uses the concept of extended trellis, which means that we run on 2 trellis diagrams parallelly, which essentially means that we have a 2-dimensional trellis structure. One is for the CRC and one is for the use of the VITERBI decoding. So as we know that CRC can be implemented in hardware using some flip-flops and some XOR gates using a feedback loop, where the output of one flop goes into the input of the other one, and then we have a feedback loop, we have an XOR gate. So depending on the kind of generated polynomial we are using, we can actually represent CRC in terms of a trellis diagram. So again, there are 4 different states because this is CRC2. And the next state, these green lines represent the transition if the input is 1. So if the message input is 1, the next state would be 1, 0 with the output as 1, 0. So we can represent CRC, cyclic redundancy check, in the terms of trellis. And then let me quickly discuss what this extended trellis and modified VITERBI algorithm, which I have been talking about in all the past slides, means actually. So here what we are actually trying to achieve is that whenever a new bit is received, there is a transition from state A to state B, okay? And then if the received bit is 0, then there is a transition between state A and transition from state A to state B. Now if the received bit is 1, then the CRC state does a transition from state A to state C, okay? Again for the trellis, if the received input bit is 0, the transition is from alpha to beta. If it is 1, it's from alpha to gamma. And then this is the extended trellis, which is kind of a 2-dimensional trellis, which has these 2 trellis diagrams running in parallel. But again, if there is a stuffed bit encountered, right, because we have bit stuffing also going on here, and that's exactly why we require the concept of extended trellis and the concept of modified VITERBI algorithm. So we need to modify the VITERBI algorithm to account for the bit stuffing which is going on. And then this bit stuffing, since we have stuffed separate bits into the input received in the input code word, we have to modify the VITERBI algorithm in such a way